I'm John McGuigan, and I'm a biologist here at Soft Genetics. And in this webinar today, I'm going to take you through the Dispersion and HMM Algorithm, which you can use for CNV discovery and NextGENe. This is a coverage-based algorithm, so our end goal will be something like what you see here. This is a tumor normal comparison, and you can see that this is the ratio between the coverage in the test project and the control project. And you can see that some regions are highlighted in red, where the ratio is lower, and some regions are highlighted in green, indicating duplications, where the coverage in the test sample is higher. So from this, we can get an idea of where our deletions and duplications are. So in this coverage-based detection, what we do is we define our regions of interest, which can be usually for targeted sequencing our amplicon locations. And we count the reads, either using normalized read counts or RPKM, which is a more standardized measurement of coverage. In either case, the results between the two methods will be essentially identical. So after we get the coverage in the test sample and the control project, we calculate the total coverage, and we also look at the ratio in each region. As a quick example here, you can see 3 regions of interest, A, B, and C. The coverage is different between the 3 different regions, the total coverage, but the ratios here are what's important. You can see that A and C are close to 0.5, where the coverage is pretty much the same in the sample and control, indicating that the sample is normal. But in the B region of interest, the ratio is about 1/3 because the coverage is lower in the sample, and this indicates a potential deletion. So where do these ratios come from? The expected copy number versus the total expected copy number. In the sample, for a duplication that's heterozygous, we'd expect at least 3x, whereas the normal control would be 2x. So our ratio would be 3 out of 5, or 0.6. And in a similar way, we can see that normal regions in the sample would have a ratio of 0.5 because it's 2 out of 4 total, and heterozygous deletions would have a ratio of 1 out of 3. More extreme duplications or deletions would have even more extreme ratios, so they'd be even more likely to be called in this case. Our problem is that our theoretical distribution has only a few different ratios that might be present. But in the actual real-world data, you can see that there's a lot of randomness to the ratios in any given region. So the question is, how do we get the signal from the noise? There are 2 parts to this algorithm. The first is dispersion. This is our numerical measurement of the amount of noise. And this lets us generate a statistical model of coverage and copy number and how they relate to one another. The HMM stands for Hidden Markov Model, and this will take that statistical model and calculate the most likely copy number state for each region based on that model. So dispersion is our numerical value for the amount of noise. And to give you an idea of what that means, here we have what some real data looks like. You can see it as sort of a triangular shape, where at the top we have lower dispersion, where the points are concentrated around that central value of a 0.5 normal ratio. Whereas at the bottom, there's a much broader distribution, and this would be a high dispersion. The way this dispersion is actually calculated is we start with a small value and iteratively increase that value until we find a reasonable confidence interval that matches our data. So we have 3 different examples here. The top row has a low dispersion value of about 0.008. And this gives us a pretty narrow confidence interval. You can see the beta distribution is graphed. And a 95% confidence interval in this case means that we'd expect 95% of the normal data to occur somewhere between 0.41 and 0.59. Whereas as the dispersion increases, we assume that there's a broader distribution of even the normal data, so our confidence interval also expands. The dispersion for one region is a little bit harder to conceptualize. What we do is we get the list of regions where each region has a ratio and a total coverage, as we saw earlier. We sort that data based on the total coverage and break it up into groups of regions of roughly equal size. So we might have the 200 regions with low coverage, 200 regions with medium coverage, and so on. And we measure the dispersion for that group of points. And what we end up with is these fitting points that each represent a few hundred regions and the amount of noise and the approximate amount of coverage in those regions. And we perform a linear fit to figure out what this relationship is so that we can see for a given level of coverage, we expect a certain amount of noise. Here's an example with real data. On the right side, you can see in blue are these fitting points where we summarize groups of regions that have similar coverage and measure the amount of dispersion in that group. And then we fit this line, this green line, to those points. And on the left, you can see the red lines show the boundaries of the confidence interval that's based on that dispersion value. And you can see how at the top it's more narrow, where there's less noise, and at the bottom with lower coverage, it broadens out. There are two different fitting methods. The first is automatic, which is what I just described. The one thing you'll have to set is the number of fitting points to use. This will be estimated automatically, but you can customize it. Ideally, we have at least 4 or 5 points to get a good idea of the shape of the linear equation. But we do want to have many regions represented in each point. So generally, small panels, less than 500 regions, might not work well with automatic fitting. But you also have the option to use manual fitting, where you can enter in the parameters for that equation manually to try and fit it by eye. Or what's usually simpler is to enter a single value to use for all regions, so that no matter what the coverage is, you're assuming that there's a certain amount of noise. Here's an example of that manual fitting, where we set all regions to use a dispersion value of 0.01. And this is a good chance to see whether or not we have good fitting. So on the left side, you can see that we have 99.72% of our regions within the fitted interval. And in this case, we have a 98% confidence interval. So if anything here, we're underfitting. We're being cautious. And on the right side, you can see the same thing, where our fitted equation, which is now a vertical line because we're using one value, is to the right. It's estimating higher dispersion than the actual measured fitting points in blue are. So what is the effect of dispersion? What do we do with this value? If you have a lower dispersion, as you see on the left here, we get a much sharper peak around the middle ratio. We're a lot more confident that the ratio we're seeing is more indicative of the rate of the copy number ratio. So here you can see for low dispersion value, we are very confident, 98.25%, that if you got a value of 0.5, it's a normal region. If there's a little bit higher dispersion in the middle, a value of 0.02, you can see that we're still fairly confident. We say that there's a 70% chance that this region is normal, but there's also a chance that it's a duplication region that just happened to have a lower ratio than it normally would. Whereas if it's very high dispersion, we really can't be confident whether it's a deletion or a normal or a duplication. We're slightly more confident that it's normal because it's a ratio of 0.5, but we really can't be too confident about that one individual point. And this is where the hidden Markov model comes in. For each possible state, duplication, deletion, or normal, we have a probability of seeing that observed ratio. And we have these measurements for each region that we're looking at. And so for each region, we normalize these measurements to 1 among the 3 possible models. So as an example, if one region is said to have a 0.35 ratio and a 0.04 dispersion, we can plug it into our equations and estimate that it's most likely to be a deletion, about 72% chance. And this isn't too surprising since a expected deletion ratio is 0.33. And as part of this hidden Markov model, we also model probabilities of transitioning between these states. If we get CNV regions, we expect them to group together and perhaps have larger CNV regions and not have them randomly scattered throughout our genome. The probability from going from a normal, if one region is normal, that the next region is a CNV, either duplication or deletion, that's related to our expected CNV ratio, which is a setting that allows you to tune the sensitivity of the algorithm. And then once we're in a CNV region, the probability of transitioning back or continuing that same CNV is 50-50. When I say transitioning back or continuing, that's the same type of CNV, either duplication or deletion. For the purposes of the model, we do not allow a duplication to occur directly next to a deletion. You could have a duplication followed by a normal followed by a deletion, but the likelihood isn't great within the model. So essentially, this hidden Markov model combines all of this information and generates the most likely calls for each region. So the reason we're using this as part of the algorithm is that it's good at smoothing out the data and removing random noise where you might have a single region in between many other regions, where that single region just happens to have a very extreme ratio. So in that case, we can often exclude that because it appears to be random noise. And on the other side, we can have hidden true variance, where we have many regions in a row that have some small increase in probability of a given state, but nothing where it's very obvious. However, when you look at the consecutive regions as a whole, the probability is higher. We convert those initial probabilities that we calculated to 3 different scores for deletion, duplication, and normal, so that normalized likelihood is in a simple to understand Phred score, where 10 would be equivalent to 90% chance, 20 would be equivalent to 99% chance, 30 would be 99.9, and so on. And we cap those scores at 80. The expected CNV percentage that I mentioned will end up increasing the scores in all the regions if you set it higher. So as I said, it's an adjustment on the sensitivity, and it's also used as a prior probability in this model. As far as the performance of this algorithm goes, the resolution depends on the region size. We're making one call for each region. We're not trying to find exact endpoints of CNVs. And if you do have a CNV that doesn't completely cover a region, what we would see is that the ratio would be somewhat in between. So if half of a region is deleted, we'd expect that deletion that region as a whole to be in between deletion and normal. The sensitivity and specificity will depend on a few different things. The amount of noise in the data, if it's a very clean comparison where the sample and the control were part of the same sequencing run, the library was prepared at the same time, that will usually help reduce the amount of noise and make us more confident in our calls. Also, again, the amount of expected CNV setting. This will affect the confidence of any one CNV that we calculate, and also it'll affect the dispersion measurement where we're calculating the amount of noise. This tool is very easy to use. What you do is open the CNV tool from the Comparisons menu in the NextGENE viewer. You would select Dispersion and HMM, and you can select to use either normalized counts, which we recommend because they're more intuitive, or RPKM, which is a more standardized measurement of coverage. And either way, those two methods will have essentially identical results. On the next page, you load your sample, your test sample, and your control project, or you can load multiple control projects. And When you load multiple controls, you can select to use the best match control, so the one where the coverage is most highly correlated to the test sample, or we can make a synthetic control using the average values or the median values for each region in all the control samples. On the next page, we define our regions of interest. In most cases, you'll want to load a bed file that lists what your targeted amplicons were. If you have whole genome sequencing, you can select an incremental segment length. So every 10,000 bases or so can be defined as a region. Or you can use built-in annotation, looking at things like coding sequences or genes or mRNAs. On the next page are our fitting settings. So you can select automatic fitting or manual fitting. You can also filter out regions that may have a higher amount of noise if there's low coverage or if it's a short region. And this will filter those regions out before we perform the fitting and analysis of the data. There's also, as mentioned before, the expected CNV percentage, and also the estimated sample purity, which is very useful for tumor data, for example. And what this will do is adjust the expected ratios to be more similar to normal. If you're not expecting to have a pure sample that has CNVs, you might have, say, 70% of the DNA in the sample will show the CNV, and the other 30% will be normal. In that case, you would expect ratios that are more similar to the normal ratio of 0.5. The last page is just report settings to control what information is displayed in the report, and also to do some simple filtering based on the final calls and scores. But now I'll perform a demonstration using some Haloplex data with manual fitting, as we saw earlier in the webinar. As described earlier, you can find the CNV tool in the Comparisons menu of the NextGENE viewer. On the first page, we will select the method that we want to use, in this case, normalized counts. On the next page, we load our sample and any controls. In this case, I'm just loading a single control, but I could have used multiple controls and taken the best matching control or a synthetic control made of average or median counts. To define my regions, I'm loading a bed file that describes my targeted amplicons. This is the best way to run the analysis when you have targeted sequencing. In this case, it's a rather small panel, so I'm doing a manual dispersion value of 0.01. When you're running this kind of analysis, generally you can run a comparison or two to get an idea of what the noise looks like, adjust the dispersion to what looks like a reasonable value, and then use that for the rest of your samples. Here I've made a change from the default. I set the minimum region length to 100 bases because that's approximately what the read length was, and regions that are shorter than the read length may be more noisy, have more variation, that makes it hard to measure. My expected CNV percentage was left at the default of 5%, and my estimated sample purity was left at the default of 100% because I'm not working with a tumor sample here. Here I've deselected normal and uncalled just for ease of use in seeing the deletion and duplication regions. I click OK and wait for NextGENE to run the comparison. As you can see, it was fairly quick in this case because these are just two relatively small projects. I had one amplicon that had a CNV called. In this case, it was a deletion in amplicon 255 in the KCNH2 gene. And I know, because this is a validated sample, that this is actually a real deletion in this exon, in this case the 11th coding sequence. Here we can see there are 635 total normalized reads. And if we look more closely, you can see that there's about 203 in the sample and about 435 in the control project. This gives us a ratio of about 0.32, which is very close to what we expect for a deletion. The deletion score is almost 30, so that's a fairly confident deletion. The normalized likelihood in this case would be about 99.9%. Our CNV calls are hyperlinked, and if you click on them, they will open the link in the database of genomic variants, so you can see if there are any known CNVs around this region. If we click this button, we can take a look at the graphs, so we can double check our fitting results to see if they're reasonable. And in this view, we can click the highlight region of interest and select a chromosome. In this case, I'll select chromosome 7. And you can see that the points are zoomed in at the top, and the points from that chromosome are highlighted in the bottom. So we can see that this region that was called as a CNV, as a deletion, I know this is the region because the ratio is low, is well outside our fitted confidence interval that we set with our manual fitting value. It's not useful in this case because we only have one called region, and it's a relatively small panel. But in larger projects like exome sequencing, the block CNV report can be useful. What this does is it combines consecutive regions, if they have the same call, into one longer call. You can also make an adjustment to the setting here where you can ignore small individual regions, so maybe 2 or 3 regions in a long stretch of a larger number of regions that have different calls to try and smooth out the data even more. The report can be saved to a tablet limited text file. The report settings can be adjusted after running the analysis. So here I will go ahead and display the normal and uncalled regions. And you can see that every region in our bed file will get its own call, either normal, uncalled, deletion, or duplication. And as long as it's not uncalled, all of the original information will be there for total reads and ratio and the scores. So here you can clearly see that many of these regions were called as normal, but because of the noise, we're not supremely confident that these are normal. Most of them have fairly good scores, so we're over 90% sure that many of these are actually normal copy number regions. You can visit us on the web at softgenetics.com. We have more webinars on other topics available through the Analysis Corner link. And you can find specifics about other topics through our application notes. For more information, you can contact info@softgenetics.com. Thank you.